exponential growth and decay. And the second part of what we're going to do today is, or maybe next time, is modeling data, which is just a a calculator application. So the first thing we talk about is modeling exponential growth and decay. The formula for that is f of t is equal to some value where we start. Remember, the subscript of 0 in science always means an initial value, so it's an initial amount, times e to the kt power. Now that should look really familiar to you. It looks like that finance formula. Remember this one says the amount of account is equal to P, e to the RT power, where P was the original amount, the principal, right? So it's the exact same formula that we've already used. It's just that we're going to take this application and use it somewhere besides just money, because it works in other places besides just money. Yes, sir? Oh, I don't care. All right. This is for exponential growth or decay, either one. Okay, it's the same formula. The only difference is this K right here, which is our rate of growth. Remember that was the interest rate before when we were doing it with money. It's just the rate of growth. If K is a positive number, then it is a growing entity. It is growing. If K is less than 0, then it is something that is getting smaller. So this is a decay. Okay? Any questions? And then we just use that formula. I've got that written down. Let's go to checkpoint 1. Checkpoint 1 says that in 1990, the population of Africa was 643 million. By 2006, the population had grown to 906 million. Okay. A says use exponential growth model. A is equal to A sub 0 times e to the kt power, in which t is the number of years after 1990. So t is the years after 1990. Find the exponential growth function that models this data. So, if t stands for the number of years after 1990, then what's my a sub 0 here? Remember, what is a sub 0? The initial amount. So if 1990 is my beginning point, 643 million is my beginning population. Okay? Everybody understand that? And then we have e to the kt. Now, that's my basic formula. The only thing that I'm missing out of my formula is I need to know what K is. I need to know what rate of growth they've got going on here. They didn't give me the rate of growth, but they did give me another point, right? Well, no, I'm going to put this in here. What does A stand for? The new population, right? And what does T stand for? The years it's been since 1990 that I could get this population. So, do you see something there that we could use? In 2006, we were at 906 million, so I can say 906 has to be equal to 643 times e to the k, and it's 16. K times 16 power. Okay? Now I'll be able to find K. So if they give me another point, if they give me the beginning and then they give me another point, I can find the rate of increase. So what do I do here? Divide both sides by 643 before I take the ln. I am going to take the ln of both sides. You're exactly right. But remember, before I can take the ln, I want to get the thing. That's right. I always want to get rid of that thing, whatever's times are added to the number that's being raised to the power. Okay? So this is going to give you a decimal. 1.40 is equal to e to the 16k. Is that good if I do it that way? So k times 16. Now, I am going to take the ln of both sides. So I've got the ln of 1.4 is equal to the ln of e to the 16k. So why did we do that? That just disappears, right? When that's not e. The ln and e cancel each other out, but that's the only time that you can cancel out. If it was the ln of 2 to that, it wouldn't. The ln of whatever that number was. Yep. But since it is e, they just cancel out, and it becomes 1. And so 16k times 1 is just 16 times k. So I have to divide by 16. So k is equal to 0.0214. All right, and so that's k. It asked me, though, for the exponential growth function. So I want to go back into my equation. So I've got a is equal to 643 e to the 0.0214 t. Okay? When I ask for the equation, what they're asking you to find is the k. And then you just write it back in there with the k and the a sub 0 in it. Because the new amount and t need to be variables. They need to stay variables. Because, you know, the new amount's going to change as the time changes. In this situation, if this models our population growth, then the k becomes a constant after you find it. Okay? Everybody understand? All right, and then part B on checkpoint 1 says, by which year will Africa's population reach 2,000 million or 2 billion? So you would take that formula that you just found for part A, and you'd put in 2,000 because we did it in millions, right? You wouldn't use 2 for 2 billion. When you want the population to be that. So you're looking for what year? So t is my variable. So how do I go about solving this one? Same way I solved the last one, right? I'm going to divide by the 643. And I get some kind of decimal. 3 point what? 11. All right. And then if I take the ln of both sides, I got the ln of 3.11 is equal to the ln of e to the 0.0214t. And the ln and the e do what? Cancel out. And so I've got the ln of 3.11 is equal to 0.0214t. And I divide by 0.0214. So t is equal to whatever that is. 2,043. You got 2,043 when you divided that? Or is that what you got after you added the number back to 1990? Okay, so you got 54.03, so it's 54 years. Now remember, t was the number of years after 1990. So you have to take 1990 and add 53 to it. You got 53, not 54? Huh? Because it was 2,000 million to get 2 billion. could. I don't know. I don't know why some of you are getting 53 and some of you are getting 54. Are you being, yeah, it might be that some of you kept the 3.11, that's 2,000 divided by 643. Okay, so 53.01 wouldn't round up to 54. It'd round up, that'd just be 53. I understand what you're thinking is if it's a part of a year, but again, it does matter on round-off error, so we always go back to just the closest one. Okay, so let's do 53. And if you add 53 back to 1990, that's 2043 is the year. Okay? Well, 2 billion people, that would be the population of Africa if something doesn't change. It keeps following this same trend. Yep. Yes, sir. Yes, ma'am. Sorry. Well, he was talking to me. Uh-huh. It's a good way to check. Good thing to check. All right. Now, check point 2. We're going to use the same idea about this decay. It says strontium-90 is a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have measurable amount of strontium-90 in our bones. We've all absorbed some amount of radiation. So, part A says the half-life of strontium-90 is 28 years. Everybody understanding here what a half-life is? Means half of the substance will be gone. So if you start out with 5 grams, then in 28 years you'll have 2.5. If you started out with 10, after 28 years you'll have 5. So in other words, the more you start out with, the more you get rid of in that time. Because the way these things get out of your system is that it goes out in half-life. Your medicine is the same way. Actually, yes, theoretically, there will always be some in your system. It just becomes such small amounts that it's negligible. But that is why a lot of medicines have long-term side effects. You know, they talk about Tylenol. Tylenol is very hard on your liver if you take lots and lots of it, because after a while, that little bit of medicine that's left over kind of starts adding up. It starts causing a little bit of damage. So, yeah. Okay. Now we want the exponential decay model for strontium-90. So anybody got any ideas? We're going to come up with the equation. Which equation are we going to use? All right. It is going to be negative because we are doing a decay, so expect K to be a negative number. Let's think about this for a minute. This is the original amount, and this is the new amount. What is that going to divide out to every single time if I'm working with the half-life? 0.5. It's actually a decimal, but it's a particular decimal, right? Because if I start out with 100, I'll have 50, right? And when I do 50 divided by 100, I'm going to have 0.5. Think about it for a minute. Everybody understand? Okay. If I start out with 20, I'll have 10. And when I divide it, I'm going to have 0.5. So anytime you're doing a half-life problem, then you're going to get this simplification. Okay? So it tells me that my half-life happens in 28, so T in this problem will be 28, and they'll give that to you. If they give you the half-life, then that's what they're giving you, is the time it takes for this ratio here to be 0.5. Then you can use the ln thingy, and the ln of 0.5 is equal to the ln of E times 28K. So the ln of 0.5, or a half, however you want to write it in there, divided by 28. A divided by A sub 0 is 0.5. If it's a half-life, we've taken half of it. So if I take, it'll always be 0.5. It's just a shortcut. What is it? What is it? Yeah, this cancels out. We got the ln of 0.5 is equal to 28K, and then I got to divide by 28. Yeah, I made magic happen, didn't I? Whoops. Sorry. Negative 0.025. And we came out with a negative number, which is nice, because we said we should. So my half-life formula here that they wanted me to get, lost. It does want that, right? Yeah, the exponential decay problem. So A is equal to A sub 0 e to the negative 0.025 t. And since it wants part B, says suppose that a nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. So what is that? What's the 60 stand for in my formula? No. The initial value. There's 60 grams floating around the atmosphere, so that's the A sub 0. How long will it take for this to decay to a level of 10 grams in the atmosphere? So where does the 10 grams go? In A. So my formula becomes 10 is equal to 60 times e to the negative 0.025 t. Going to be more than 28 because I've lost more than a half-life, right? Because the first 28 years would be down to 30, right? And in the next 28 years, I'd be down to 15. So it's actually going to be something more than 56, right? You understand what Devin is saying? Exactly right. Now, we can go through and actually solve this, though, without having used our math sense. I'm very proud of you that you are. So what do? We divide by 60. So I get 1/6 is equal to e to negative 0.025 t. Then I take the ln of 1/6, and that's equal to the ln of e to the negative 0.025 t. The ln of e cancel out. So I've got the ln of 1/6 is equal to negative 0.025 t. And then I got to divide by negative 0.025. So t is equal to what? What do we get when you plugged it in? 71.67. So nearly 72 years. That is a long time. Yep. That's what it is. And you're exactly right. What happens is that you can't live in that area. No one can live in that area for probably longer than that. Yeah. Where'd you steal those from? Where'd you steal those from? Now. Huh? Huh? It doesn't. It doesn't. they have not truly found any substance that totally keeps that radioactivity contained forever. And so,
People that do mess with it are...
yeah. All right. So the next type of growth model that we want to talk about is logistic growth model. Those formulas are given in this form. Where C, A, and B will all be numbers. Now this model is used, can you see that it's got a little bit of exponential growth in there? See it? Everybody see my little piece that looks like my old exponential growth? What's going on with this is that, remember we might have talked about it with this group, I don't know, I talk about it usually. When we start talking about population growth and I tell you that E came up, you know, as a matter of studying some things in nature, and one of the things that they saw was like with the rabbits, there was rabbits that had been set loose on this island and they kind of watched how the population grows over a period of time, and they actually was able to prove that population of animal growth follows this E, this E that we came up with, this is irrational number, does actually apply in nature as well as in like when cells multiply. Well, what they noticed was after a while you stopped having exponential growth. So remember we talked about this because after a while the rabbit population was so large that the food and stuff started really, the supplies and resources started getting really limited. And rabbits especially are really cool in that when there's not enough resources for the next generation to, they absorb their babies. They don't actually have babies, they just kind of absorb them back into their body.
Yeah, maybe like 3, nope.
So, well, when the resources get better and the females are able to eat plenty of resources, then they're able to go ahead and carry the babies to term. They don't matter. So anyway, so a logistic growth model looks like it follows the exponential model for a while, but then what happens is it kind of levels off. Because we find that in just about every population, as resources get smaller, even with humans, you know, because we start using artificial methods to limit the number of children we have. Because you can't afford to have a family of 10 anymore like they used to be able to when they worked a farm, and the more kids they had, the more free labor they had, the more food they could grow. So they could support those kids because they could work more land and get more food in. Well, we don't have that happening anymore. Now we work in factories and we work in jobs, and the more little mouths you have to feed does not mean the more little mouths, the more little hands you have to go out and work. Because we can't send them out and work in factories anymore when they're babies because they made that illegal. Not that you'd want to, but you do understand this logistic growth is more real. And so they came up with a new function. Now the nice thing I'm going to tell you about this is when they give you population growth, or they talk about this logistic model, you never have to come up with the equation like you do on the exponential growth. So they give you the formula and you'll just plug the numbers in that they tell you to plug in. So if you'll look at checkpoint number 3, you'll see what I'm talking about. It says in learning theory project, psychologists discovered that f of t that equals 0.8 over 1 plus e to the negative 0.2t is a model for describing the proportion of correct responses after t learning trials. Okay, so in other words, as people got more and more chances to learn, it starts tapering off, like you're going to get as many as you're going to get after a while. So, find the proportion of correct responses prior to any learning trials taking place. So T is equal to what in that situation? Chance to learn. Watch a lecture. Chance to learn something. A learning trial. Yeah. So if it's before any learning gets to take place, what would T be? 0. So you put a 0 in for T. And anything to the 0 power is 1. Very good. So I've got 1 plus 1. So I've got 0.8 over 2, which is 0.4. So about 40%, before you learn anything, if you're just guessing, most people can get about 40% of the test right. Okay? Just on luck. Some people can, some people can't. Part B says find the proportion of correct responses after 10 learning trials. What would you do? Put 10 in for T. Put 10 in for T. Now, do you have to solve that equation? That's not an equation to solve. So like I say, honest logistic learning models, for the most part, they just give you information and you just plug it in and you just work the problem out. Okay?
0.70.
So, like I said at the beginning, the only thing we didn't get to is the modeling data, the last piece. Your assignment for this section is on page 479. And you need to do 2 through 54 even.